So in that particular situation, we're really seeing that we have a new system. We had our old system where there was no potential from 0 to A. Now we actually have an electric potential on our charge. Okay, so we're adding something. So there are two ways to try to find the solution, the quantum mechanical solution for an electron placed between two plates in one dimension, right? And so let's see if we can figure that out. First of all, anytime you want to solve Schrodinger's equation, you write down H psi equals, what's the other part over here? Time part. I H bar is the time derivative of psi. And then the first question you ask, is the potential a function of time? Is it? No, so that means it's separable. We'll be able to pull the time piece out of this. This is x and t. So we say, we're going to be able to pull the time out. So we really only have to solve this thing, and the time part's going to go out. Okay. There's going to be an energy. So what are we trying to do in this problem is what we've done previously, and all the other problems that we've done in Quantum 1, and partly in this course, is we're trying to find these things, but for a new system, for a new Hamiltonian. The first thing we have to do in order to solve this equation is find a Hamiltonian. So what is the Hamiltonian for this? Yeah. Oh, thanks. That's a good idea. Hey, low tech. Yeah. No remote control. So what do we have to do here to solve this? Well, we have to first find a Hamiltonian. Thanks. Anytime I do that. Okay, so what would the Hamiltonian be? What's the kinetic part? Yeah. P squared over 2m. Right. And then what's the potential part? Did we have a potential part in this guy over here? No, there wasn't one. So this one's going to have a potential. And what's it going to be? It's going to be this thing right here. Q E and that's going to be equal to the energy times psi x. And so our goal is, oops, I'm a little out of control there. H is that. So our equation will be P squared 2m plus Q E naught x psi of x, okay, equals E psi of x. Great. Okay, that's what we're trying to do. Okay, this looks like a relatively unintimidating equation. Let's just write this out. This is supposed to be a what? A minus h bar squared over 2m, second derivative with respect to x. Differential equation. Right? So we're really trying to solve an equation that looks like the following. Okay, so if you take a differential equations course, they're always rewriting everything to a different form. Okay. We're really trying to solve a differential equation that looks like x minus so that's the differential equation. Doesn't look very intimidating, does it? Kind of like second order differential equation, right? You know the solution? You didn't do that one in differential equations? There's a minus in here. Sorry. That's energy, not, I should be using script D. Not for the electric field, okay. And this is E naught, Q E naught. Because this is an E and not going to be a linear solution difference. We're not going to worry about this too much, but anyway, the solution turns out to be a really hard thing to solve. The solution to this are a bunch of Aries functions, okay? And it's pretty darn complicated. It'd be like more like an advanced differential equations course to solve this equation. And this is obviously not very complicated, right? I mean, we just added a potential to it. So the question is there another way? Now, fortunately, there is an analytical solution to this. And you can imagine just small tweaks to this potential. This is an infinite potential, so this is a small tweak, right? If you've got infinite walls, any electric field is a small tweak, right? You're comparing infinity to whatever, some electric effect. It's going to be a small effect. And so the question is there a different approach we can take to solve this that doesn't cause us, every time we change it, we say, oh, you know, I'm going to change this. I'm going to make these parabolic plates, you know. I'm going to come over here and I'm going to do the following. And because the thing I'm working on looks like this, I'm making a space electrostatic deflector and stat. I've got really weird fields that are kind of radially. You know, my function no longer looks like this. It looks more like R or some crazy thing. Okay, and there's a theta and phi component. It's real complicated. And it's a small effect compared to my infinite square well, which is really bound right in there. And I asked the question, like, what's the wave function energy states for that? Okay, it turns out there are only a handful of quantum problems you can actually solve. And you do most of them like in quantum 1, 2 in graduate school. Then you're done. There aren't any more analytical solutions left. In fact, you could sit down, write a book, and people have done this, theorists, pretty much all the reasonable quantum problems that can be done analytically. And then after that, you're out of luck. And all of those problems are the really interesting ones. The ones where you have little tweaks, okay? You do something goofy like this. Why would you do something goofy like this? Well, if I got an atom, I got the hydrogen atom, and I put it in an electric field, what happens? Isn't that a good question to ask? I got my little atom. It's in an excited state. I put it in a little electric field. What happens? Wouldn't you like to know the answer to that? That would be a good thing to know. Why would you like to know that? Well, it turns out anytime light goes by an atom, it can cause a transition to occur. Sounds like a really reasonable thing to want to understand. What happens when you perturb a well-known system with some kind of external effect? And this is an external effect. Is that really clear in your minds? Because we're going to dive off the deep end, and you can get lost in the notation. You'll forget why the heck they're even doing. I don't know what I'm doing. It's weird. I don't understand any of the stuff you're talking about. Just go back to this. Say, if I had a system that I know the answers to, can I find new wave functions? And so the system that I know the answer to gets it, they get names, they get special names. They get little knots up here. Okay? And when you put that little knot there, it's not e to the 0 power, it's a name. This is the 0th order. The 0th order is known. You've already done the problem. We did this problem. We know the 0th order. Okay? What we're trying to find is this new thing. These are the new things. New. New things. That's what we're trying to find, the new things. Okay, so we have two things. We have the old things, the knots, and we have the new things. They don't get any little symbols or anything. Okay? So keep that in mind. Always have your eye on the ball when you're looking at these equations. It's going to get wild. There's just going to be hundreds of terms flying around. You're going to go, oh, I'm lost in the jungle of quantum mechanics. Don't. Go back to your home base. Your home base are going to be your knots. Go. There's a it's a jungle out here. I got to find the knots. Where are they? Oh, there's one right there. There's a knot tree and another knot tree and the knot energy. Find them. They go, what was the thing I was trying to find? It's these guys that don't have any little things stuck on them. No numbers or slashes or whatever, any crazy names. So all you have to remember is You start with these because you know them, but you're really trying to find these. You're trying to solve this problem, okay? And then there's all this stuff in between, which is going to be the confusing jungle. I'm going to take your hand and walk you through the jungle so we get to here, okay? And it's going to turn out, when I walk you through the jungle, it's going to be like this. Suppose I'm trying to get to this thing, okay? And I know this thing. I know everything. I know the energy of this thing. I know the state of this thing. I know everything about it. But that's the problem I'm trying to solve. What I'm going to do is this. I'm going to say, I know this, but if I add this much more junk to it, I get that close. And if I add a little bit more to it, I get that close. And if I add a little bit more, I get that close. And pretty soon, I'm pretty darn close. And each one of these chunks is a correction to this. I take this and I say, well, this almost looks like that. They're both carts. But if I come over here and chop a little off, I'm getting close to that. Okay? And if I make it not as wide, I get even closer. And so what I'm doing is I'm taking the thing that I know, modifying it by adding little functions to it. Eventually, I'm getting pretty close to the real thing. If I get close enough to it that it looks almost like the real thing, and all the measurements I make on it give me the real thing, I go, I'm good. That's enough. I could go infinitely long and adding little corrections. But usually that first chunk gets me really close. I'm almost there, and I go, oh, that's tiny. I don't do any more work because the result is pretty close to what I'm measuring. This is called perturbation theory, okay? We're going to take a known system. We're going to perturbate it a little bit. This perturbation is by adding some additional force or field or potential to it. And we're going to ask the question, what is the result of that? We're not going to try to solve this. This is too hard, okay? Because the Hamiltonian is crazy. It's not even that hard for this one. There is a solution, but it's a crazy solution. This is way too hard. I'd rather just go back to the one that I know, which is the H naught, psi naught, E naught, psi naught. I know everything there and say, you know, that's hard. But I know everything about this. I'm so happy with this. I'm just going to jiggle these guys a little bit and see how close I get to the real thing, which are those, these are the real things. These are the real answers. But I can't get to them because they're so hard. I say, well, I'll just take these and add little bits to it till I think I'm pretty darn close to this. Okay, it's not as satisfying as solving Schrodinger's equation where you get the answer. This is the answer, okay? What's the answer? That's the energy. What's the wave function? That's the wave function. This is going to be different. You're going to write down the Hamiltonian, and then you're going to go, I couldn't get this. It's too hard. Yeah, that was really hard too. I can't get that. I don't know how to do the math. No one knows how to do the math. Okay, it's not that I don't know how to do it. No one. Get the best mathematician. They can't do it. They can't solve the differential equation. So what you do is you go, well, but I really need this. This is important. So what you do is you go, you know, it's pretty darn close to this. So what I'm going to do is just add a little bit of extra wave function to this and see how close I get to that. Does that all kind of make sense to you? Okay, good. Because that's what I'm hoping it's going to do. Okay, so now I'm going to go to my PowerPoint, which is going to be a little higher level, but hopefully, you know, you'll like it. Okay. Luis, can you see that okay?
Yeah.
Okay, great. Okay, so what we're going to talk about is real true quantum theory. We're on a roll now. We're on the quantum theory roll. And what I want to point out here is normally what we do in quantum mechanics is we find a Hamiltonian, which has a kinetic energy. Good. That's where I screwed the R. So, so we solve this equation, okay, and which is very elegant when you think about it. H times that and E times that. It's pretty cool. And the H has the potential and the kinetic energy involved in it. The problem, of course, is that, let's see if I can go to full screen on this. Luis, can you still see this if I go to full screen?
Yeah, I can.
Okay, is it full screen for you?
Yep.
Okay, great. So, for example, we'll use a real example here. If we look at the Hamiltonian for the hydrogen atom, it kind of looks like this, okay? And we've already solved it, okay? The game was, we know H, let's find psi and E, and we did. We spent weeks, okay? Fletcher spent some time, I spent a whole bunch of time. We got angular momentum out of it, we had all kinds of stuff. Pretty cool. Yay. Ooh, okay. Oh, that's that, what's his name, guy? Who's that? Homer Simpson. Yeah, Homer. Look, he's doing calculations with it. Hey, Homer. Okay. So Homer is did some calculations just like we did, and we got some crazy solutions, okay, for the YLMs, and we got the energy. That was a real tour de force to get to that point. And we put a tremendous amount of work into that. Well, we didn't. Really smart people did. And we learned how to understand it, okay, what they did, which is very cool. And that human beings were capable of actually understanding the simplest atom and write down a function that describes it is pretty darn amazing. Okay, and we learned stuff about angular momentum and the projection of the angular momentum. It was very exciting times. But as we perform more experiments, and other smart people discover stuff, we realize that the electrons moving about are 1% the speed of light. So we have to correct, and we're not going to do it right now, but we have to correct the actual kinetic term, which isn't really right relativistically, but we've got to add on this term. And this term in itself isn't totally correct. There's actually more terms to the expansion of the relativistic correction, but they go as the square of this quantity, each interval. So the next one would be p to the 6 and p to the 8. And since these are small effects to start with, when you square a small effect, it even becomes smaller. So we're not going to consider higher order terms. So this in itself isn't even a correction for the Hamiltonian. It is just a good approximation for the correction of the relativistic term. If you want to treat this relativistically, you have to solve even a harder equation, the Dirac equation. So there's that relativistic effect. There's this other piece that we just talked a lot about, L dot S. L dot S comes into play because we have mu sub S, two magnetic moments that interact with one another. And depending on their orientations, we add a little chunk of energy, which has to go into the Hamiltonian. This, in fact, is the Hamiltonian. It contains all the energy information. Then there's another term which talks about when you get in the ground state of the hydrogen atom, these two things give you a wrong answer unless you correct it with something called the Darwin term. And we'll come around to that and talk about why that exists. So, oops, we did all that work on the hydrogen atom, and it's not really right. When you make measurements, all the energy levels are slightly off. Something is wrong. There's an other external pieces have to be included in the Hamiltonian. Just like over here, we did this, but then we said, oh, it's in an electric field. It's not quite the right answer. So we have to add this extra potential to it. Over here, we're adding actually two extra potentials. Here's the basic hydrogen atom. We added two potential terms and a kinetic term, a relativistic kinetic term. And so by doing that, we will effectively change the answer. So to do this totally correctly, you take this whole mess, you stick it in here, and you solve for psi and E. Guess what? You can't do it. There's no mathematical expression. In fact, it's not even right. People tried and made all kinds of other approximations when they were trying to solve it. And people like Hartree and Bach worked on it, and Born worked on it. Lots of people, really smart people, worked on this stuff. And they came up with different approaches, but all of them were approximations. Dirac solved this part of it. He got the right answer. Actually, this falls out too in Dirac's equation. So this whole thing gets done in Dirac's equation, but it's really hard to solve. So using this method of perturbation theory, we're going to answer this. We're going to say, instead of trying to put H back in, solving that differential equation, we're going to say, oh, this stuff is small. And we know it's small, right? Because when we go measure the effects, they're really small. They're like, these guys are on the order of 1/10,000th the energy that you get from this part. Okay, it's a really small effect. That, these are very small effects. So you go, oh, they're small effects. So maybe I can just go back to this piece, use the wave functions I already have, and just say, well, how about if I just play a little bit around with those wave functions and their energies? I'll get something that's pretty close. So what's the method for doing this is the real question. Okay, so the idea, this thing's kind of a pain. The idea is that in a classical sense, they didn't invent perturbation theory for quantum mechanics. It's been around for a while, okay? And the reason why it's such a powerful tool, if you have, for example, 200 years ago, people would look at the Earth, the moon's orbit around the Earth, and say, it's not quite perfect. There's small little effects. Well, one of the effects was the sun interacting with the moon, other planets interacting with the moon, caused small perturbations of its orbit. Today, where perturbation theory is very valuable, you put a satellite up, and it's in an orbit somewhere between Earth and the moon. It's not just a simple orbit for the satellite because the moon perturbs its orbit. Now, for some of those, you can do the full-out calculation numerically, and they do that, or you can use perturbation theory, okay? You can take the orbit and perturb it slightly because of the moon's influence. Depending on where the moon is relative to the satellite, it can be very accurate. If the satellite is close to the Earth, it is in fact a very, very accurate way to determine the satellite's orbit, okay? If the satellite is very close to the moon, then it's not, okay? To the degree that if it's orbiting the moon, it's a really bad approximation for an orbit around the Earth, because it's not orbiting the Earth anymore. So you have to actually use it appropriately. Okay, so the new method is this. It's the Hamiltonian, this Hamiltonian right here, the one that we're trying to solve for our problem, is now going to be broken up into two pieces. It's going to be broken up into the Hamiltonian we know and love, and we know the solutions. Why do we love it? Because we know psi and E for it, so it makes us happy. We're very content with that, those guys over there, the knots. So this H naught is known, its size are known, its energies are known. This H is the perturbative Hamiltonian. It would be maybe this piece or this piece or this piece or all of them, but normally we would just take one of these and ask the question, if we had this perturbation on this existing system here, so we would take this and put it in there, what would the effect be, okay, on psi and E? Okay, where does this actually arise in real physics experiments that are interesting to us as physicists and have helped us to better understand the nature of atoms? So certainly LS coupling, okay, that would be spin orbit coupling. That's that U sub L, U sub S, dotted into each other, give us some potential energy. How does that affect our energy level? The Stark effect. If we put an external field outside of our system and look at it, how does that affect our wave functions? How does it affect transitions between states? The Zeeman effect. You have an effect where you put your atom inside a magnetic field. Since it's orbiting, things can change, right? It's almost got a little magnetic moment. You put a little magnetic moment in a field, it's going to have an effect on your hydrogen. How does that change your spectrum, your energy transition? Does it make the energy greater or less? Does it split certain levels? So this is a way to actually split LS coupling and see what that actually does to our state. This is very interesting stuff, and we learn a tremendous amount about the atoms by looking at the Zeeman effect. There are other things, the anharmonic oscillator. If you have something that has a spring constant K, but it's not linear in K, okay, so as you stretch it, it kind of changes K a little bit. That might be very applicable to things like quarks inside of a nucleus. They kind of almost act like a spring in there. As you pull them farther and farther out, more and more energy needs to be put into the system because the spring is storing more and more energy until the spring actually snaps. And when it snaps, you end up having a quark with some spring on it, another quark with some spring on it inside the nucleus. This quark goes out, but there's sufficient energy now to form an antiquark. So you have a quark-antiquark pair, which in fact is a meson. And inside the nucleus, a quark is created from the energy, the excess energy, by stretching that string. And that thing rounds out the 3 quarks that are normally in something like a proton, or 3 to 5 quarks, or some odd number of quarks. So this is an important thing. Nearly free electron problem. In solid state physics, you have electrons, okay? And they move around through materials. It turns out that you can do some very nice modeling, very accurate modeling of how solid state devices work because of this. Okay, so what we're going to do next week is I'm going to talk about the H knots for all of those, okay, which are going to be pretty straightforward. Okay, we're going to talk about the actual mathematical perturbation that goes with it. Each one has some kind of mathematical perturbation, which represents the field or the effect. And then just go back and look at what the actual Hamiltonian H naught is for each one of those. So for a spring, it looks like this, but the anharmonic looks like x to the 4th. Okay, for this guy, which is a particle in a magnetic field, okay, here's my magnetic field. The J is the current density, which is generated by having something that moves around, an electron orbiting in a magnetic field, produces H prime. And but this is our standard potential that we know from the hydrogen atom, hydrogen atom, hydrogen atom. But these are the different effects that we're going to get from each one of those. So we talked about a few of them today. We're going to talk more about them. The really cool, interesting physics is here. Okay, this is the cool stuff because this is where you can take an atom, stick it in a magnet, and see what the heck you're going to do to it, or an electric field like we did over here. We can actually affect it in some way and say, what should happen to the states? What should happen to the energies? And then go measure those energies and see if we're right. Is that okay? Did you guys kind of follow that? Okay. I'll see you guys on Monday. Sorry that we have to delay the presentations. I know you were all hoping to do them on Monday, but have a good weekend. Stay safe. And if you get a moment, you might send Hunter a note. He, contracted COVID. I don't know how he's feeling, but send him a note. Say, hey, how you doing?